Hello again, everybody. We're looking now at our material for week 8, which is the second portion of chapter 6 out of the textbook. And what this section is looking at are sampling distributions. Sampling distributions are used to estimate our population proportions. Usually we're looking at means and proportions. We're looking at estimating those parameters with these sampling distributions by selecting a standard sample size and using that. So the key concept here is that we're looking at not just the original population anymore, we're looking at sampling distributions. We're looking at the statistics based on samples. And part of the key of this is we must select a sample size that we're going to be using. And of course, we're going to call that sample size n. And what we do is we select all samples, all possible samples of size n. Now the key thing here is it's with replacement. So just because an item is in the first sample doesn't mean it can't be in the second sample. And then we're going to calculate the statistic of that sample. So if we're looking at estimating a mean, we're going to calculate the mean of each of those samples. If we're looking at estimating a proportion, we're going to calculate the proportion of each of those samples. And it's those items, those sample means or sample proportions, that make up the sampling distribution. So general behavior of a sampling distribution, when we've done this, we selected that sample size and taken all those samples, the sample proportions tend to be normally distributed, and the sample means also tend to be normally distributed as well. The mean of the sample proportions is equal to the population proportion. So if we take all of the possible samples of size n, we calculate the proportion in each of those samples. We find those proportions that we found are the sampling distribution. If we then find the mean of all those proportions, it will be equal to the population proportion. So here's an illustration, a visual. If we have our sample proportion, our population proportion, P here, and then we take all of our different samples, we can see here some of them are going to have a proportion smaller, so population proportion is right in the middle of this curve. Some are going to have a proportion that's smaller. P hat, by the way, P with the little hat over it, that is a sample proportion versus P, which is the population proportion. Some of them will be smaller than the population proportion, some of them will be larger, but they average out. The mean of them becomes the population proportion. The same will be true if we're dealing with means of those samples. So obviously the proportion is for categorical data, so it either has the trait or it doesn't. The mean is for numerical data, so we're taking a bunch of values and average them together, calculating it out. Same thing. This center of this curve is mu, the population mean. X bar is the sample mean. Oops, my size got screwed up there for a second. You see some of the samples have means that are smaller, some have means that are larger, but again, when we combine them together, the mean of the sample means becomes the population mean. Population variance is not normally distributed. You'll notice both of these were bell curves. The proportions of all the samples, the sampling proportion tends to be normally distributed, or a bell curve. And the sampling distribution for the sample means, those tend to be normally distributed or in a bell curve. For sample variances, they do not. Now in this course, we're not going to focus on sampling distributions of sample variances. This distribution has a curve that is skewed, usually off to the right. It is not a normal distribution. It actually uses what's called a chi-squared distribution. Again, that's not going to be part of this course. Stepping back here, population proportions or sample proportions, those will always be normally distributed. So it's going to be a normal distribution. The sampling distribution for the sample means will either be normally distributed or use the normal distribution. And it's always going to be normally distributed, but sometimes the behavior can be tracked with the normal distribution. Sometimes we're going to have to use something called a t-distribution. And all a t-distribution does is it accounts for is if we don't have certain information available to us, like if we don't know the population standard deviation, we can use the sample standard deviation, and the t-distribution accounts for the fact that the sample standard deviation is almost always smaller than the population standard deviation. So let's look more at sampling distribution for sampling distributions for proportions or for sample means. And we're looking at sampling distributions of sample statistics. And they always tend to be normally distributed with the center of that bell curve being the population parameter, whether that's the population mean or population proportion. And it comes down to selecting that sample size n. So we take all those possible samples of that size from the population, and it's from those samples then that we draw the sampling distribution. This again is done with replacement, and we'll go over why that's important later on. So the sampling distribution of the sample proportion. So we're using this trying to estimate the population proportion. We take all of those possible samples of size n again, and we find the proportion from each sample. Those proportions are the sampling distribution of the population proportion. It can be represented with a probability histogram or a bell curve. I prefer the bell curve like we did up here, just because that illustrates that idea that it is normally distributed a little bit more clearly. So notation when we're dealing with proportions, remember n was the size of the sample, x was the number of successes within that sample, capital N is the size of the population, x divided by little n is the sample proportion. Remember that's p hat, that little hat on top of it says that's the sample proportion. And then x over capital N, that is the population proportion. Anytime we tend to see a mark above a variable, like p hat or x bar, that is telling us that it is a statistic from a sample rather than a parameter from a population. So some behavior of the sample proportions. Again, they tend to be approximately normally distributed. And their target value, again, the target value means the center of that bell curve is the population proportion. So if we were, an example here would be rolling a die. So we're going to consider a success rolling an odd number. So that'll be a success. So we're going to roll a die 5 times, and we're going to get 5 results. Within each sample, we're going to calculate then what proportion of them are odd. So let's say we roll 2, 4, 3, 1, 6 in our 5 rolls. Well, there are 2 of those that are odd, so that's 2 out of 5. That would be a 0.4 sample proportion. The next roll, we might roll a 5, 2, 1, 4, 3. There are 3 numbers there that are odd. That's 3 out of 5, or a 0.6. And we can keep doing this over and over again, and we would generate all these different sample proportions. Well, when we were all done, we would take all of those different sample proportions and find the mean of those, and the mean should equal the population proportion, which is 0.5. In the population of the numbers 1, 2, 3, 4, 5, and 6, all the possible results of rolling a die, there are 3 out of those 6, or 0.5 proportion, that are odd. We would expect the mean of our sample proportions to give us the same result. So here this is just illustrating that if we were to take those different possible values, could anywhere be from 0.0 up to 1, You can see the center here. The graph gets a little small on screen here, but you can see the center of that is at 0.5, the population proportion. So we can see the values 1, 2, 3, 4, 5, or 6 are all equally likely when rolling a die. Because of that, the population proportion is 0.5. Half of them are odd. So that's our theoretical or classical probability. Also turns out to be the population proportion. And so then the mean value of that proportion from all of our samples is going to calculate out to be 0.5, if we do it enough. So now let's switch over to the sampling distribution of the sample mean. So here, doing the same concept, we're picking that sample size, and we're taking all possible samples of that size. We're finding the mean of each of those samples, the X bar. So the mean of the X bars, sometimes labeled X bar because it's the mean of all the sample means. And that the mean of all those sample means should be equal to our population proportion, to mu, our population mean, which is mu. So again, the behavior of the sample means, they tend to be normally distributed again. We'll discuss how we know that later on in some of our further sections of the textbook. The target, again, is the population mean. So those sample means will form a bell curve, normally distributed. The center of that bell curve will be mu, the population mean. So again, let's go back to rolling a die. This time, rather than counting how many of the numbers are odd, we're going to add them up and find the mean result. So let's say we had 2, 4, 3, 1, 6 again. So if we add those up, we've got what? 6, 12, 15, 16 divided by 5 gives us 3.2 is the mean for that sample. We might have 5, 2, 1, 5, 4 is our next 5 rolls. What do we get there? 7, 8, 17 divided by 5 gives us 3.4. And we keep going. All these samples here, all these sample means, if we add those up and find the mean of them, we should get a mean of 3.5. Because if we take the values on the die, 1, 2, 3, 4, 5, and 6, again, they're all equally likely, so there's no need to weight them. If we added those up and divided by 6, we would get a mean of 3.5. So here's a little bit of an illustration of that. You can see here is our graph, a histogram of all of our different totals, and the center of that is this population mean of 3.5. So based on those possible values being equally likely, that's how we got the population mean of 3.5. We just added up 1 through 6 and divided by 6. The 10,000 just means we took a large enough number of samples. We can't just take 3 or 4 samples and expect it to average out to the population mean. We have to take all of the possible samples, or in this case, since the die is generating a new amount each time, just enough samples so that we can reasonably expect it to be close to the population mean. So I'm going to give you a better view of this based on, so the die example is a little contrived because there's an unlimited number of results there. So let's take a look here at a sample. This is a sample, or a population, sorry, with big N equals 5. There's 5 items in this population. The mean of this population, if I add those up and divide by 5, is going to be 9. Standard deviation, make sure I'm using the population standard deviation, is 0.4. So now I'm going to choose a sample size. And what I'm going to choose is just little n equals 2. So I'm only going to select my samples. I'm only going to select 2 items from this population. So all my possible sample size, I would have 3 and 7 would be one possible sample. 3 and 9 would be another sample. 3 and 11, and 3 and 15. Next, I could have 7 and 9, 7 and 11, 7 and 15. I could have 9 and 11, 9 and 15. And finally, I could have 11 and 15. So first, this illustrates what I mean by with replacement. The 3 can't be in the sample twice because there's only 1 3 in the population. So it's not with replacement within each sample. Each sample is uniquely selected from the population. But before I choose the next sample, those are all put back. So 3 was in the first sample, but it can also be in the second sample. There's replacement between samples. So let's find the sample mean for each sample. So I got 5 for the first one, and I'll just go down the list here. You can see some of those are significantly smaller than my population mean of 9. Some are significantly larger. If I find the mean of all the sample means, I should get 9, my population mean. So you can see there the mean of all the sample means comes out to equal the population mean. Now we'll talk more later on about the standard deviation of those sample means, and that'll also be related to our population mean, but not quite as neatly as that. So we're not going to deal with the distribution of the sample variances, so we're going to skip over those few slides there. And then we'll talk about an estimator. So the purpose of all this is we want to get to where we can estimate the population parameters. So when I talk about an estimator, what we are typically talking about is an estimator of a population parameter. Because the whole reason we're doing this is because we don't really know those population parameters, so we're trying to use these samples to give us an estimate. An unbiased estimator is one that targets the population parameter. Now that's the phrase that this textbook uses, is targets the population parameter. All that means is when I make the distribution of those estimators, the mean of all those estimates will be the population parameter, whether it's the population mean or the population proportion. It will be at the center of that distribution. So if we're estimating a proportion, P hat is going to be centered around P, the proportion of the population. If I'm estimating a mean, that sample mean of X bar is going to be targeting or centered around mu. Variance, same thing. It's going to be centered around the population variance. Again, we're not doing this estimator here, but sigma squared. These 3 items are unbiased estimators. They will give you, even though the variance is not normally distributed, it is that chi-squared distribution, it still tends to be centered around the population variance. Not all of our statistics are unbiased estimators. So these 3, the proportion and the mean and the variance, are used because they're unbiased estimators. The median, the range, and the standard deviation are not unbiased estimators. The median tends to be all over the place compared to the sample medians, the mean of the sample medians compared to the population median. The range is always smaller. And the standard deviation is always smaller. So we can't use those for estimating population parameters at all. So it is important to make sure standard deviations, even though they're not an unbiased estimator, if we take a large enough sample, the larger the sample gets, the closer the standard deviation does get to being a good estimator. So we often will use it for an estimator. We use a correction factor. And that's where we talked about that t distribution instead of using a normal distribution. The t distribution corrects for the fact that sample standard deviation is not an unbiased estimator of the population standard deviation. So why did we sample with replacement? We talked about this a little bit when I showed the Excel example there. We sample with replacement so that our samples are all independent of each other. Once we've selected one sample, that doesn't affect the chances of an item being in our next sample we select. So it's just a matter to keep things independent and make sure we are including every possible combination of numbers from the population in our samples. So a discussion of sampling distributions leads us right into the next section discussing the central limit theorem. So the central limit theorem is building on what we mentioned about how the mean of the sampling distribution targets the population parameter, but it also then goes into the standard deviation of the sampling distribution and how that relates to population parameters. So the key concept here in this central limit theorem is that we're using a normal distribution based on these sampling distributions being normally distributed. So first of all, if we're looking at estimating a population mean, if the sample size, whether the population is normally distributed or not, if the sample size is 30 or larger, the sampling distribution of the sample means of X bar can be approximated with a normal distribution. So that's significant there. I mean, it makes sense that if the population is normally distributed, that the sampling distribution of the sample means would be normally distributed. But what this is saying is that even if the population is not normally distributed, if we take a large enough sample, and it's commonly accepted that that sample size has to be greater than or equal to 30, in this textbook saying greater than 30, which is fine, the sampling distribution is still normally distributed. Which is huge as far as allowing us to use this process, this calculation to estimate population parameters. So here, the central limit theorem for the distribution, the sampling distribution of X bar, or the sample means, is saying that a population with a mean of mu and a standard deviation of sigma, even if it's not normally distributed, we can, as long as we have a big enough sample size. And we're taking simple random samples of size n. We're taking all of the possible simple random samples of size n. The notation we're looking at, of course, the mean of the sample means is sigma X bar. That's going to equal the population mean. Standard deviation of all those sample means is this was mu of X bar. This is sigma of X bar, and that is related to the population standard deviation. But remember, the smaller sample, smaller size group, it's typical that the standard deviation is going to be smaller as well. So the standard deviation of all those sample means is going to be the population standard deviation divided by the square root of the sample size. The bigger the sample size is, the less variation or less standard deviation there will be in the sample means. So smaller samples, there's going to be a lot more variation in those sample means. Bigger samples, there's going to be very little variation in those sample means. So our practical rule, as we said, either the population has to be normally distributed or the sample size has to be bigger than 30. So before we apply this, that's one thing we should always check. Is the population normally distributed? If it's not, is the sample size greater than 30? If it's not, then these methods do not apply. We can't use them. So it's always wise to check those requirements. Is it normally distributed? Or if it's not normally distributed, is the sample size bigger than 30? Before we proceed to do all this analysis. Also, we need to consider, are we looking at an individual value from within the population, or are we looking at the mean of a sample? Because that changes the calculation as well. If we're looking at a single value, then the z-score for that value is simply the value minus the population mean divided by the standard deviation. If we're looking at the mean of a sample, the z-score for that mean, it's still the sample mean minus the population mean, but we have to adjust the standard deviation by dividing by the square root of n. So further notation here. We saw that we've already seen that the mean of the sample means is mu of x bar is equal to the population mean. The standard deviation, sigma of x bar, is the population standard deviation, or sigma divided by the square root of n. This is often referred to as the standard error of the means, or SEM. I'll refer to it as the standard error quite a bit because that's what I'm used to. So an example we're going to look at, Boeing 737. Their planes have 126 seats in the main cabin. In an attempt to create more room, the engineers are playing with the idea of reducing the width of the seat from 16.6 inches to 16 inches. 0.6 of an inch doesn't sound like a lot of reduction in width. We have the information that the average male, we're assuming males are larger on average than females here. So we're going to use the average male hip width is 14.3 inches wide with a standard deviation of 0.9 inches. Let's use that then to answer a couple of questions. Our first question is, what is the probability that a randomly selected adult male? So this is a single individual. We are not looking at the mean of a sample here. The second one, find the probability that 126 main cabinet seats are all occupied by males with a mean hip width greater than the 16 inches. So this is talking about a sample mean. The 126, even though it's a full cabin, it is a sample of all airline passengers. So we are looking at the mean of a sample, or sampling distribution there. And then asking for design sakes, which one is really more relevant and why? And we'll look at that discussion after we're done with our calculations here. So first, A, as we said, that's an individual value looking at what's the probability that randomly selected person is wider than 16 inches. So I'm going to go to Excel here. And we're going to do our normal distribution function here. And our value is 16 with a mean of 14.3, standard deviation of 0.9, and it is true, not cumulative. Now remember, this is going to give us the area to the left. So looking at this curve here, what Excel is giving us, if this is our cutoff of 16 inches, is giving us this area over here. So we get 0.97055. They just rounded it to 0.9705. Here, I'll show you that if I expand this out, it's actually 97054.6. So the 0.9705 is correctly rounded. We want the area greater than that to the right of that, so we have to do the complement. 1 minus that gives us 0.0295, or approximately 3% of men would have hip widths larger than that. If we wanted to use the table, we would have to do a z-score. We would take the 16 minus the mean of 14.3 and then divide that by 0.9, giving us a z-score of 1.09, or 1.89, I should say. Looking up in the table in the book, you would find 1.8 here, 0.09 up top. That's going to give you that probability of 0.9706. Slightly different, we had 0.9705 because this again is rounded off because that z-score is rounded to 2 decimal places. Subtracting gives us, again, the 0.0294, which is really close to our 0.0295 that we had from Excel. So it's still only about 3%. Question B, what is the probability that the mean of a sample of 126 males is bigger than 16 inches? Well, first, this is normally distributed because hip width is normally distributed. But even so, our sample size is 126, which is bigger than 30, so it doesn't matter. We don't have to verify that it's normally distributed. Our mean, we're targeting 14.3 as the population mean, so we're targeting that as the center of our sampling distribution. And now, since we're looking at a mean of a sample, we have to find a standard error. So it is the 0.9 divided by square root of 126. Now when I do that calculation here, 0.9 divided by the square root of 126, I get 0.08017. If I wanted to be really precise here, I would use the 0.08. But remember, this textbook is using rounding to 1 decimal place for 1 place beyond the data here. So the 0.0 or 0.1 is what we're going to use for this standard error. That's going to cause some significant round off errors. I'll show you the difference as we do the calculation. Still, going to be pretty much the same answer that we get. So here's our curve. Again, the center, 14.3. We want to know the probability of being greater than 16. Again, Excel is going to give us this probability here, and we're going to have to convert it. So in Excel, use my norm dist function again. Now, the first time I enter this, I am going to do 0.9 divided by the square root of 126. I can put that formula right in there. I don't have to have it down to a single number. And I'll get 1. I can expand that out. It's still going to come out to 1. In other words, it's not 1, it's like 0.9999999, but it's so close to 1 that Excel can't distinguish between them. If I use the rounded value that we got from dividing out that standard error of the means and getting the 0.1, well, it'll be 16, 14.3, 0.1, and 1. I'm still going to get 1. So even though that 0.1 here that we had for our standard deviation of the sample means is really like a 0.08. It's been rounded. It doesn't really significantly change our answer at all here. So because that is 1, what it's saying is it's so close to 1 that there's almost nothing left. We want that was the probability of being to the left here. We want the probability to the right, so we're going to find the complement. 1 minus 1 gives us 0. That little plus there is telling us that it's actually slightly greater than 0, but it's too small to even be measured. So 0 plus is saying it's extremely tiny probability. If I want to use the tables in the textbook using the z-score tables, well, I use 16 minus 14.3 and I divide it by the 0.1. I get a z-score of 17. Well, I believe the table only goes up to a z-score of 3.49. And if you look at that probability, it's a 0.9999 probability. So 17 is going to be way larger its probability of being less than 17 is going to be even bigger than 0.9999. But we'll just use that as an estimate for now. Finding its complement would give us 0.0001, which again is almost zero. So again, all we're saying is the probability that the cabin of 126 people would have a mean greater than 16 inches is extremely small, almost impossible. So then down to the final question, which is more important for this example? Is it the mean of the cabin? We'd say, well, yeah, as long as the total fits in, we're good, but not necessarily. The seats are only going to be 3 people at a time, three people side by side. So what would matter is if the 3 people in the seats average to less than 16 inches. But so the more important calculation here is the individual. About 3% of individuals would be larger than 16 inches hip width. Now that seems like a really small number. We talked about 5% being a significant percentage before, but remember that 5% is based on the situation. It can be varied with the situation. Here, out of 126 passengers, if I had 3% of them, that would mean almost 4 passengers per flight would be too large for their seat. And of course, that could cause some issues loading the airplane and challenges where there'd have to be some sort of adjustments made, moving them next to someone smaller or moving them into finding a larger seat somewhere on the plane. So that individual, the probability of an individual being bigger than 16 inches is probably the more important probability here. And even though it's only 3%, it's significant enough to say maybe we don't want to reduce the seat. Now, if this were a full analysis, we'd go back to, well, let's go back to the 16.6 inches that we currently have. And how would that change the probability? What percent of people? Let's do that calculation just to compare. So if we leave it at 16.6, that probability of someone being smaller drops down to 0.5%. So from 3% to 0.5%, which means basically on average, you'd have less than 1 person per flight that would be larger than the 16.6. So at most, you'd expect to accommodate 1 person per flight. So that makes that probability drop significantly smaller. So there is a significant difference staying with the 16.6 inches of width. So this is all part of the whole idea of central limit theorem and sampling distributions is to lead us into a couple of concepts coming up. One is confidence intervals, which we talked about estimates a little bit before. Confidence intervals are another way of estimating our population parameters. And hypothesis testing. Hypothesis testing is where we use a sample to draw a conclusion about the population. And recall when we did probability in week 3, we talked about rare events or unlikely events. And if we make an assumption, in this case, we made the assumption that the sampling distribution, that the mean of the sampling distribution is equal to the population mean. If we make that assumption and we get a result that is either significantly higher or significantly lower than what we expected, to the point where the probability of that happening is very, very small, then it's the assumption that was most likely incorrect. And there's only 2 possibilities there. Either the assumption was incorrect or we got a really, really, really weird, unusual sample. And so we assume that it was just the incorrect assumption rather than a very unlikely sample. So an example of this would be body temperature. It's commonly accepted that human body temperature is 98.6 degrees. Studies have shown on large data sets that it's a standard deviation of about 0.62 degrees Fahrenheit. So if we take a sample of 106 subjects and we calculate their mean, we're finding the body temperature of each subject and we find a mean of 98.2. Is this significantly low based on the assumption that the human body temperature averages 98.6. So what we're doing here is we're taking a bell curve, a normal distribution. We're saying 98.6 is the center of that distribution. And we're saying, well, is 98.2, what's the probability of getting a sample mean that's smaller than that? So we have our population mean, or we're expecting the mean of our sample means to equal our population mean of 98.6. We're expecting the standard deviation of those sample means to be the population standard deviation of 0.62 divided by the square root of our sample size, giving us 0.06021997. And we'll go ahead and calculate that probability here. So normal distribution, 98.2, given a mean of 98.6, and point, I gotta find that. What do we have here? 0.06022, I'm going to call it. It gives me now that E negative 11 at the end of that is saying that in scientific notation, saying it's really, really small. What that really is saying is 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Basically that. Notice when I hit enter, it gives us right back to that notation. That E negative 11 is saying times 10 to the negative 11th in scientific notation. So we find that probability of being less than 98.2. If we use the table in the book, we would get a z-score here of negative 6.64. Again, the table only goes to negative 3.49, and that probability is 0.0001. So this probability has got to be smaller than that. So all we can say is the probability is less than 0.0001, which is very unusual. It's definitely less than the 5% benchmark we discussed earlier. So we would say that either the sample was a really bad sample or the assumption was incorrect. And so we tend to go with the conclusion that the assumption was incorrect. So it shows that the temperature that we assumed of 98.6 is extremely unlikely, or getting our sample of 98.2 would be extremely unlikely if we stuck with the assumption of 98.6. So we're saying that most likely the mean temperature is really not 98.6. So either we conclude that we got a very, very rare sample, that's this possibility, or that the actual mean body temperature is not 98.6. And that's what we conclude. It's actually probably closer to the 98.2. Finally, if we are doing this, finding the standard error of the means, we're assuming that we're dealing with an infinitely large population. That formula where we say that the mean of the sample means is the population mean over the square root of n. That is assuming that we have an infinitely large population. Or at least really large compared to our sample size. And by really large compared to our sample size, we're saying that the sample has to be less than 0.05 times the population size, less than 5% of the population. If it's greater than 5% of the population, then we have to use this finite correction factor, this symbol here. Remember, capital N is the size of the population, little n is the size of the sample. The reason I wanted to show that to you is to go back to our example we used in the last section here of this population of 5 numbers, where we took all possible samples of size n equals 2, and we got the sample means. Well, let's find the standard deviation of the sample means. Now, this is all the possible sample means, so it is a population standard deviation. We find that. Now, this will be smaller than our population standard deviation. It always is. Smaller size group usually has smaller standard deviation. If I were to take my standard formula, which is to take the population standard deviation divided by the square root of my sample size of 2, I'm not going to get this number here. I have to use the finite correction factor. And how that works is I take this number here, the population standard deviation divided by the square root of n, and I'm going to multiply it by the square root of capital N, which is 5, the size of my population, minus the size of my sample, which is 2, divided by the size of my population of 5, minus 1. And there you see I get exactly my standard deviation of the sample means. So that's after the finite correction comes in that we get that to actually work out. It would be very laborious to use a larger population to show you that if the sample size is less than 5% of the population, that we don't need the finite correction factor to make the standard deviation of those sample means equal the population standard deviation divided by the square root of the sample size. Here, sample size of 2 with a population of 5, our sample size was 40% of the population. But this does illustrate that this does work out. So this tool of these sampling distributions and this central limit theorem is going to be what we use going forward for the next several sections to analyze our data sets and draw conclusions.